Hello, this is Gene Gallagher from the Department of Environmental, Earth, and Ocean Sciences at UMass Boston. This will be an analysis of Case Study 8.2, Breakdown Times for Insulating Fluid Under Different Voltages, a controlled experiment with Matlab. And so I've already downloaded the data from the Cengage site as Excel spreadsheets. I've used the function dataset from Matlab to load those as dataset arrays within Matlab, and then I've written the program to access that dataset array. And so I'm just going to run the program. We'll take a look at the code, and then I'll run the program again. So the program is Ramsey Schaefer, RSCS 0802 third, for the third edition of Statistical Sleuth. There are the data. This is a breakdown time of fluid. Here is a diagnostic plot, just a linear regression that you get of log of breakdown time versus voltage for the insulating fluid. And so this one's not a publication quality graphic, but it does give you an idea of the fit, and the fit appears to be quite reasonable. And so let's go through the other diagnostic fits. We'll give you a plot of the residuals, and the residuals look just fine. Maybe a little bit of a left skew. Here's the normal probability plot of the residuals, and there's a little bit of a departure from normality, but not severe. No severe outliers in the data set. Here's a plot of the fitted values versus the residuals, and there's no apparent problem. They look fine to me. There's no trumpet-shaped pattern. It looks fine in terms of a fit. In this model, we're going to be fitting the ordinary least squares regression, and since we have replicates at 1, 2, 3, 4, 5, 6, 7 different voltage levels, we can do a full goodness of fit test. So the full publication quality graphic, you can put in the 95% prediction band, as I've shown here, such that at each level of voltage, this gives you the band that should contain 95% of the individual observations. And then I have the equation given for the log breakdown time is 18.96 plus or minus 3.81, and then minus 0.507 plus or minus 0.114. That one's probably using at least one too many significant figures, but that could be changed fairly readily. And actually I may change that when we go in and look at the code. There's another example from the chapter when they state that would the data be analyzed by a square root transform instead of a log transform. So I also fit the data with a square root transform. So here's square root of breakdown time, and you can see the fit looks pretty bad. And in here, all of these points are lying outside of the confidence bound. These points are considerably outside the confidence bound. Here's the plot of the residuals, and then there's some really extreme outliers on the square root scale. Here's the normal probability plot, and there are 3 observations all up here that the residuals are way different from you would expect from a normal distribution. Here is the plot of the fitted values versus residuals, and here you get a classic wedge-shaped plot or trumpet-shaped plot with the residuals at much higher levels away from the fitted values. So this is not a good fit compared to the log model. This is a nice graphic showing it, and I've kind of wasted my time producing a nice graphic of a bad fit. But here's the fit of the square root breakdown time. I did this because you can fit the lack of fit test to the square root breakdown times to determine whether there are departures from the regression line that are greater than you would expect by chance. And in this case, you can take a look at the lack of fit tests. The lack of fit test with the log scale actually fit the lack of fit test. These are the regression parameters, and you can fit an ANOVA model. This is the regression parameters just on fitting voltage as a continuous variable. Breakdown time is the response. R squared, not great, 51%. Adjusted R squared, 51%. Here's the lack of fit test where you do an ANOVA on each one of the 7 groups, and then combine the sums of squares from the ANOVA and the regression analysis and calculate the lack of fit F statistic. It has it's 0.5. The expected value is 1, so the p-value has to be greater than 0.5, and the p-value is 0.77. Here's the model fit with the square root of voltage, square root of breakdown time as the response variable. as a function of voltage. And the lack of fit test for that analysis is a very, very small p-value, 0.000304. So not only qualitatively did the diagnostic statistics look bad, but also the classic lack of fit statistic looked bad. So now we can do edit RSCS0802 third and bring up the data file. This is just loading the case study 802 dataset array. I loaded it, the dataset array. It was saved on my hard drive as RSCS0802 third as a mat file, as all of the datasets from Statistical Sleuth. They're all saved as mat files after I translated them from an Excel spreadsheet. This, I created a new dataset array with a log transformed response variable. I fit it with a linear model fit, and it's just one call to basically fit the models. This is classic kind of object-oriented programming, so linear model fit. And then I calculate the lack of fit F statistic in 2 or 3 lines of code after pulling out the appropriate lines from the ANOVA table. Plotted the residuals, and then I fit the model for the, this is 30 or 40 lines of code, is just printing that graphic, including plotting the prediction intervals. And then here is the fitting the square root voltage, case study 802. This is, I created a new data set array with the square root of the breakdown time, fit that model, and then plotted it. I mentioned that the significant figures were, there were too many, so let me just find that. That's an sprintf statement, a C programming convention that's used to label graphs. So sprintf, here's the breakdown time, and instead of reporting it with 4.3 degrees of freedom, I'm going to report it with 3.2 for the F statistic, and that's more than enough significant figures. 3.2 for the F statistic, and this will look a little bit better once we plot it. So now we hit F5. This will run the analysis, just these diagnostic plots. And here, this is better, that it's 18.96 plus or minus 3.81. That one I could probably cut down from 5.2 to 4.1. And then the slope is minus 0.51 plus or minus 0.11. So 2 significant figures is more than sufficient. And that's what I wanted to demonstrate.